So we have seen the field axioms which give the algebraic properties of an arbitrary field. These axioms are modeled on the familiar properties that are possessed by the rational numbers. Now I mentioned in the last module on the algebraic axioms that there are even fields that are finite. Not only that, they are very important in cryptography. Now I am going to put some more axioms that rules out finite fields also, and at the same time brings forth additional structure to the rational numbers which was so far lacking. Definition, ordered field. So we are going to put an ordering on the field. Okay, an ordered field is a field f comma plus comma dot. Of course I can denote the multiplication by dot. Last time I did it by times. It really doesn't make a difference. Along with a binary relation which we denote as less than or equal to. Okay, that satisfies certain axioms. Number one, reflexivity. This should remind you of something from the last week. For all x in f, x is less than or equal to x. 2. Total ordering. This just says that any two elements are comparable. For all xy in f, either x is less than or equal to y or y is less than or equal to x. Note, I say either x less than or equal to y or y less than or equal to x, but as we have seen in the modules on logic, whenever we use or, we always mean inclusive or. It's possible that both x is less than or equal to y and y is less than or equal to x, and that happens precisely when x is equal to x. That's the content of the next axiom, antisymmetry. Antisymmetry says that for all xy in f, x less than or equal to y and y less than or equal to x forces x to be equal to y. The only element that is less than or equal to itself and greater than or equal to itself is the element itself. And fourth property, transitivity. Transitivity just says that if x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. This is just the familiar transitive property that you have already seen when we studied equivalence relations. Now, so far, the axioms that I have listed does not interact with any of the existing field operations. So the axioms that I have listed so far is what are known as the axioms of an ordered set. Now I am going to introduce the behavior under addition and multiplication. So we have behavior under addition, which merely says that if x is less than or equal to y, then for each z in the field, x plus z is less than or equal to x plus y. Y plus z. Just a second. Y plus z. Okay. So sixth is behavior under multiplication. And as you can guess, what this is about to say is if x comma y are both greater than or equal to 0, recall 0 was our notation for the additive identity, then the product is also greater than or equal to 0. Okay. So this characterizes the properties of an ordered field. These are the 6 axioms that we have in addition to the axioms that we listed about the field properties. Okay, so we just set up some notation. If x is less than or equal to y and x is not equal to y, then we write x is less than y. Okay, note, this is just a notation. This is not a theorem or anything. This is just the notation. We define x less than y to mean x is less than or equal to y and x is not equal to y. Similarly, we have greater than or equal to. I leave it to you to formulate what greater than or equal to and greater than are. They are just followed directly from the less than or equal to relation. Okay. We also call the set P to be x in F such that x greater than or equal to 0. This is positive numbers, positive set. Okay. These elements that belong to this set are called positive, and similarly we have the set N to be x in F such that x is less than 0. Okay. So just one moment, I made a slight error. This is not x greater than or equal to 0. This is x greater than 0. Okay. So we have that an element of an ordered field is either positive, negative, or is 0. Okay. Now, I'm going to give you a fairly straightforward exercise. Again, these are just basic manipulations, will give you the proof. So let F be an ordered field. F be an ordered field. You now have to prove the following. Proof. Number 1, if x is positive, then minus x is negative. Okay. Then 2, if a comma b are in the field, so I should write if x is in the field is positive, then minus x is negative. If a comma b are in F and you have a less than b, then minus a is greater than minus b. 3, if a comma b comma c comma d are in F and a is less than or equal to b, c is less than or equal to d, then a plus b is less than or equal to c plus d. Note, this is just a minor variant of one of the axioms, but still it requires a proof. You cannot just take it for granted. 4, if a comma b are in F and you have 0 less than a, sorry, no less than or equal to, 0 less than a less than b, then 0 is less than 1 by b is less than 1 by a. The reciprocal of a larger number will be smaller. Note that 1 by a and 1 by b are the inverses of a and b. It's another notation for the inverses. What happens if you had a less than b less than 0? Think about what happens in this scenario. Another exercise is show that x is greater than y if and only if x minus y is greater than 0. Okay. Now, in an ordered field, you have familiar properties that you already know from the rational field, but certain things will require a proof. Let me state a proposition. In an ordered field, 1 is greater than 0. Okay, so this so far what we are proving are all utterly basic and trivial facts, But the thing that you should remember is that we are doing it in a new structure called an ordered field, where you have specifically listed the properties that the field has, and you're trying to derive whatever new property you want just from these basic axioms. Not only do you have 1 greater than 0, and inductively 1 plus 1 plus 1 n times is greater than n plus 1 times is greater than 1 plus 1 plus 1 plus 1 n times. Okay, so we have 1 greater than 0, and inductively 1 plus 1 plus 1 plus 1 is always greater than 1 plus 1 plus 1 n times alone. Proof. Now 1 is certainly not equal to 0, because that was one of the hypotheses in the field axioms. Okay, and by total ordering, that means either 1 is less than 0 or 1 greater than 0. Okay, suppose 1 is less than 0. Then I can add minus 1 to both sides by one of the field axioms, the behavior under addition, and conclude that 1 plus minus 1 is less than minus 1. Okay, which in turn gives that 0 is less than minus 1, because 1 plus minus 1 is just 0. Okay, now what we do is we use the behavior under multiplication. We multiply, since minus 1 is greater than 0, minus 1 into minus 1 is also greater than 0. Okay, to be precise, I can just write minus 1 into minus 1 is greater than equal to 0. I cannot actually write greater than 0, but it's not really a problem, because minus 1 into minus 1 is anyway 1. We get 1 greater than or equal to 0. But we already know is 1 is not equal to 0, so we can actually conclude 1 greater than 0. Okay, which is a direct contradiction to what we started out with. We started out with suppose 1 is less than 0, and we got 1 greater than 0. So this is a contradiction. So 1 is always greater than 0. Okay, that's the conclusion. Now the second part of the proposition about the inductive behavior is left as an exercise for you to do. Okay, now I started off by saying that these axioms of field and ordered field are all modeled after the familiar properties that the rational numbers Q have. So it is no surprise that we can actually embed Q inside any field, any ordered field. Now it's difficult for me to make these things precise, because we don't have the required background from abstract algebra. So I will take a simplistic presentation and hope that in your abstract algebra course you see it in greater detail. So let F be any ordered field. Note that I am just saying let F be any ordered field. I am forgetting that there are binary operations, plus and multiplication, and there is a binary relation which is less than or equal to. In mathematical, it is customary in mathematical literature to just forget that we are dealing with sets that have additional structure, like an addition or a multiplication or an order, and just treat the set itself as the one that has all of these built in. So I will just say let F be a field, with the understanding that there is an underlying addition, there is an underlying multiplication, and then there is an underlying less than or equal to relation. Let F be any ordered field. We can define a map from the integers to F as follows. Okay, we just set F of 0 to be 0, and if n is greater than 0, then we set just F of n to be 1 plus 1 plus 1 plus 1 n times. Note that the 1 on the right is the multiplicative identity of the field F and has nothing to do with the 1 in the integers. Similarly, we just set F of minus n to be just minus F of n. Again, note carefully the minus on the left hand side of this equation is the minus that is coming from the integers, whereas the minus on the right hand side is supposed to be the additive inverse in the field f. Okay, now we have a major theorem. The map f is injective, and not only is the map f injective, this map respects the algebraic operations. What do I mean by this map respects the algebraic operations? Well, this is where a bit of abstract algebra is required, but let me just give an ad hoc definition. It just means that for all m comma n in Z, f of m plus n is equal to f of m plus f of n, and f of mn is f of m f of n. Again, note carefully, the operations on the left hand side of both equations is the addition and multiplication in the integers, whereas the operation on the right hand side is coming from the field. If you are familiar with a bit of ring theory, what this theorem really says is that you have an injective homomorphism from the integers into any ordered field. Okay, so proof. The proof is a bit tricky. So what we will do is we will first prove the second part, that the map f respects the algebraic operations. First of all, note that f of 1 is 1. Okay. So because f of 1 is 1, it is obvious that f respects the operations when either m or n is 1 or 0. Just check that when you have either m or n to be 1 or 0, then it is obvious that the operations respect the algebraic structure. Okay. Now what we will do is, since we have shown this for when m or n is 1 or 0, we will assume that m is a fixed integer, m is a fixed positive integer, and then we will apply induction to show that for any non-negative integer, we will show by induction that f of m plus n is f of m plus f of n. We will show that addition is respected whenever m is a fixed positive integer and you take a non-negative integer n. So assume that we have shown this. We have shown this for all non-negative integers less than or equal to n naught. We are going to use proof by strong induction. Then we have to show that f of m plus n naught plus 1 is f of m plus f of n naught plus 1. Okay. But observe that the right hand side, f of m plus f of n naught plus 1 is actually f of m plus f of n naught plus f of 1. Why is this true? This is true because the induction hypothesis says that f of n naught plus 1 is just f of n naught plus f of 1. Okay. But now again, by the this is not the inductive hypothesis, sorry about that. This comes from the fact that whenever you have one of the quantities to be 1 or 0, then the algebraic operations are respected. Now, for this to proceed with the proof, what we will do is we will write this as f of m plus n naught plus f of 1. Why can we do this? We can do this because whenever you have a fixed integer m all the way up to n naught, we already know that the result is satisfied. So f of m plus f of n naught I can rewrite as f of m plus n naught. But this is same as f of m plus n naught plus 1. Okay. This is just f of m plus n naught plus 1. Okay. But what is f of m plus 1 naught? This is just 1 plus 1 plus 1 plus 1 plus 1 dot 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 plus 1 m plus n naught times plus an additional 1, which is obviously equal to the left hand side. We can argue informally also by writing f of m as 1 plus 1 plus 1 plus 1 m times and f of n naught plus 1 as 1 plus 1 plus 1 plus 1 n naught plus 1 times, and see that it is equal to the LHS also. But the formal argument with the induction is needed to make this mathematically precise. Now, I leave the negative cases as an exercise. It follows immediately from the definition of f of minus n is just minus f of n. From that, this will follow. Now, what about multiplication? Multiplication, I will just skip. Multiplication is just repeated addition. It's just repeated addition in the integers. Repeated addition. And the same thing is true in the field when you are multiplying elements of the form 1 plus 1 plus 1 plus 1 times 1 plus 1 plus 1 plus 1. Using distributivity, you can convert it to repeated additions. Okay. So by using the fact that multiplication is just repeated addition, it's very trivial to prove that the same algebraic, the operation of multiplication is also respected by the map f. Okay. Now we still have to show that f is injective. So suppose f of m is equal to f of n, then we immediately get f of m plus minus n is equal to 0. Okay, which means f of m minus n is equal to 0. Okay, now what we will do is assume m is greater than n. Why can we assume this? Well, if not, just interchange the role of n and m. If m is less than n, then just take n minus m instead. But that means 1 plus 1 plus 1 m minus 1 times m minus n times is equal to 0. But you have just proved as an exercise, as a part of the previous proposition, that 1 is always 1 plus 1 plus 1 plus 1 is always greater than 1 plus 1 plus 1 times lesser, and inductively it will be greater than 0. This is not possible. This is impossible. Okay. So the net conclusion is that you must have the map f to be injective. So the upshot is the integers are actually sitting inside any field in disguise. They are sitting as 1, 1 plus 1, 1 plus 1 plus 1, and the negatives of these, minus 1, minus 1 plus minus 1 plus 1 plus 1, so on. Okay. Now I'm going to give you one more exercise. Show that f also respects the order relation. You have to first formulate what it means for f to respect the order relation. Then you have to show that it in fact respects the order relation. So we now have a map f on the integers. We can now extend this map f to all rational numbers m by n, where n is not 0, in the following way. You can write it as f of m times f of n inverse. Okay. Now, there is a bit of checking to do. First of all, we have to check that this map is well defined. Several problems can arise. F of n could turn out to be 0, but that's not possible because we have shown that this map f on the integers is injective and only 0 goes to 0. Second thing what can happen is, recall from our discussion on equivalence classes that this representation of rational number m by n is not unique. You can write it as many different rational numbers. You have to show that the formula on the right hand side does not change if you change the representation. If you write it as f of 2m by 2n, you should not get a different value of f. It should not turn out that f of 2m, f of 2n inverse is different. That should not happen. It should give the same value in the field. That is also easy to check, but a bit tedious. Once this is done, we will know that this map is well defined. And it is not very hard to check that f respects both the algebraic as well as the order structure. F respects both. F respects both the algebraic structure as well as the order structure. And f will be still injective. F is injective. In other words, Q is sitting inside any ordered field in a disguised form, just like the integers are sitting inside any ordered field in a disguised form. In particular, in this discussion, we have shown that ordered fields have to be infinite, and all ordered fields must contain copies of Z and copies of Q. This is a course on real analysis, and you have just watched the module on order axioms.